All right, in this problem from your book, the information given are basically just, in the table here, are just the costs for shipping a unit from either plant A, B, or C to a manufacturing site 1, 2, 3, or 4. Reading the problem, we have Semiconductor Corporation produces particular solid-state module that it supplies to 4 different television manufacturers. The module can be produced at each of the operation's 3 plants, A, B, and C, although the costs vary of differing production deficiencies in the plants. That's why the table is there. Specifically, it costs $1.10 to produce a module at plant A, 0.95 or 95 cents to produce a module at plant B, and $1.03 to produce a single module at plant C. Monthly production capacities of the plants, that means how much they can actually make in a month, are 7,500, 10,000, and 8,100 modules, respectively. Sales forecasts project monthly demand, which means how much they have to produce, as 4,200, 8,300, 6,300, and 2,700 for each of the 4 manufacturers. If the cost in dollars for shipping a module from the factory to a manufacturer is shown below in the table, find the production schedule that will meet the needs of the minimum cost. In other words, we have to decide how many modules to make at each of the 3 plants and then ship to each of the 4 manufacturing sites. So that gives us 12 variables. And how your book then is using subscripts, x11, x12, and so on, is thinking of this table as a reference. So row A is row 1. So x11 will be the number of units made at A and shipped to manufacturer 1. x12 would be the number of units made at A and then shipped to manufacturer 2, and so on. B being row 2, C being row 3. So we want to minimize cost. Well, there's a lot of things that go into the cost. The book doesn't actually give you the entire objective function here because it has a lot of terms, but it gives you a hint at what it should be. So basically, what do we have? Out of the units that are being made at plant A and shipped to manufacturer 1, the number of those being x subscript 11, there's 2 costs. There's this 0.11 for shipping each unit, and then there's a fixed cost per unit of production from plant A, which is $1.10. So that's why we have $1.10 plus 11 cents times x11. And then for plant A going to manufacturer 2, we do the same thing, except we have $1.10 per unit plus, from the table, $0.13 or 13 cents times x12. So you get 12 terms just like that, but each term within x1 comma something is going to be $1.10 plus these 4 numbers. Each term with an x2 comma something is going to be the 95 cents plus these numbers, 4 numbers for those 4 terms. And then each x3 comma something is going to be the $1.03 plus these numbers from the last row of the table. Now again, there's 3 plants and 4 manufacturers. The plants have limitations on how much they can actually make. So the sum of all the variables, which are x1 comma something, has to be less than or equal to the capacity for plant A, which is 7,500. And then all the variables that are x2 comma something have to add up to a number that's no bigger than 10,000 because that's the capacity for plant B. And then finally, all the variables that are x3 comma something have to add up to something which is no bigger than the 8100, which is the capacity for plant C. At the same time, we have to fill demands. So everything that's eventually shipped to manufacturer 1, all those have to add up to the demand. Now, in realistic terms, in the book they put equals here. You have to fill the demand exactly. But in reality, you could just say greater than or equal to the demand, and you're going to get the same answer. Because in this case we're minimizing, so the math isn't going to want to choose more if it's going to increase the cost. So it won't go higher than that. But you can put equals if you want to fill it exactly. It doesn't make a difference. So the point is, all the variables that are x something comma 1 have to add up to the demand for manufacturer 1, which is the 4200. All the variables that are something comma 2 have to add up to the demand for manufacturer 2, which is 8300. All the variables that are x something comma 3 have to add up to the capacity, add up to the demand for manufacturer 3, which is 6300. And all the variables that are x something comma 4 have to add up to the demand for manufacturer 4. In this case, as always, for most of these problems, our variables have to be non-negative, and in this case they have to be integral, which means whole numbers. You can't make a fraction of a module and ship it, so you have to either make a module or you don't make it. So when that happens, that changes solutions. We'll see later how we deal with such problems, but basically the idea is pretty simple. You graph your feasible region. If it was a two-variable problem, you'd have a feasible region that you could graph in the plane. And then inside of that feasible region, you would only consider the points that have integer coordinate values as the ones you can choose from. And then you would choose the one of those that will minimize cost. This is a higher variable problem, so we can't draw a picture to do this, but we'll talk about algorithms that will actually help us figure this out.